So here we're going to start to talk about stoichiometry. All right, so what is stoichiometry? It's the study of the quantitative aspects of chemical formulas and reactions. So earlier, when we first started out talking about SI units, we introduced the concept of a mole as the SI unit for the amount of a substance. So a mole represents a quantity, a physical number of entities, much in the same way that, let's say, a dozen represents a number. In this case, it's a dozen, it's 12. In the case of the mole, it's the amount of a substance that contains the same number of entities as there are atoms in exactly 12 grams of carbon-12. And this is known as Avogadro's number, which is 6.02 times 10 to the 23rd entities, which is basically an incredibly huge number. So earlier we introduced the idea of atomic weight, the weighted average of all the naturally occurring isotopes. This basically represents the mass of 1 mole of atoms. So for example, if you have 12.01 grams of carbon, that's the atomic weight of carbon, you will have an Avogadro's number of atoms, or a mole of atoms, 6.02 times 10 to the 23rd. If you have 32.07 grams of sulfur, that's the mass that it takes to make a mole of sulfur. If you have 22.99 grams of sodium, you have a mole of sodium atoms, right? So if you take a mass equal to the atomic weight of the element, you'll have a mole of atoms, right? So it takes a larger mass to make a mole of sulfur. Sulfur's heavier than carbon or sodium. So what about compounds? All right, so for a compound, we have what's called the formula weight, and that basically represents the mass of 1 mole of molecules. So how do we get this? To obtain the molecular weight, what we do is we add together the atomic masses or the atomic weights of all the atoms in the formula. So for example, let's look at water, H2O, right? 2 hydrogens and 1 oxygen. What mass is required to get a mole of water molecules? It comes out to be 18.02 grams. So how did I get that? You take the mass of 2 hydrogen atoms and 1 oxygen atom, right? So 2 times 1.01 plus 16 is 18.02 grams per mole. For ammonia, it takes 17.03 grams to make a mole of ammonia molecules, right? So that's 3 times 1.01 plus 14.02, that's the nitrogen. That's 17.03 grams per mole. So, suppose I asked you the question, if you have so many grams of a substance, how many moles do you have? How do you do that calculation? There's 2 calculations, grams into moles and moles into grams. So let's do grams into moles. So if you divide the number of grams of a substance by the molar mass, this gives you the number of moles of a particular substance. So say, for example, I asked you how many moles are present in 78 grams of carbon. Okay, so it takes 12.01 grams to make a mole. You have 78 grams, right? So you divide 78 grams by 12.01 grams per mole. I simply multiply by the reciprocal, which is the same thing. You're dividing 78 by 12.01, and you get 6.50 moles. If you're ever not sure what to do with the two numbers, just try to reason through it. Do you divide 78 by 12 or the other way around? If you think about it this way, it takes 6.50 moles, or I'm sorry, it takes 12.01 grams to make a mole. We have 78 grams. 78 grams is bigger than 12, so your number has to be bigger than 1. Okay, now let's do this calculation for a molecule. Well, so let's say, for example, how many moles of carbon dioxide molecules are present in 11 grams of carbon dioxide. Okay, so you have to figure out the formula weight of carbon dioxide, right? Carbon dioxide, the di means 2. You have 1 carbon and 2 oxygen atoms. So that's 12.01 for the carbon plus 2 times 16. 16 is the atomic weight of oxygen, and that comes out to be 44.01 grams, right? So now our moles should be, our number of moles should be less than 1, right? Because it takes 44.01 grams to make a mole, but we don't have 44 grams, we only have 11 grams. Okay, so you take 11 grams divided by 44.01 grams per mole is 0.250 moles. Okay, so one more time, to convert grams into number of moles, you divide by the mass of the substance. Okay, so what if we wanted to do the reverse of this calculation? Okay, what we wanted to do the reverse of this calculation, converting moles into grams. Well, multiplying the molar mass by the number of moles will tell you the mass of substance present. So let's do these two calculations in reverse. Okay, so what would be the mass of 6.50 moles of carbon? Okay, we have 6.050 moles, and the weight of carbon is 12.01 grams per mole, right? Look at your unit, number of grams per mole, right? So moles times grams per mole, the moles will cancel, and that'll give you grams. So 6.5 times 12.01 is 78.06 grams. Okay, same thing, let's do this calculation for our carbon dioxide example. What would be the mass of 0.250 moles of carbon dioxide? We already figured out the molar mass of carbon dioxide is 44.01 grams per mole, right? So we take 0.250 moles times 44.01 grams per mole is 11 grams. So let's talk here now about, stoichiometry and chemical formulas. Alright, so chemical formulas express mole ratios, not mass ratios. So for example, if we look at a very simple compound like sodium sulfide, Na2S, okay, now this formula, first of all, let's talk about what it does not mean. It does not mean that there's 2 grams of sodium for every 1 gram of sulfur. This expresses mole ratios, not mass ratios. What it means is that there are 2 sodium atoms for every 1 sulfur atom, or more specifically, 2 moles of sodium atoms for every mole of sulfur atoms. But formulas express mole ratios. And if you remember when we talked about formulas, the subscript always goes with what comes before it, right? So the 2 applies to the sodium. So this formula means 2 sodiums for every 1 sulfur. Okay. What if we wanted to convert that into a mass ratio? What if we wanted to convert this chemical formula, which expresses mole ratios, into a mass ratio? Okay, that would be calculating the percentage composition. Okay, so the percentage composition is the percent by mass of each element in the compound. And we can calculate this from the molecular formula. All right, so let's do this for glucose. C6H12O6, right? So it's a covalent compound that has carbon, hydrogen, and oxygen, right? So we're going to first calculate the mass of the 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen, and add that up to get the molar mass. So we'll take, what is the mass of 6 moles of carbon atoms? 6 times 12.01, 72.06. Okay. What's the mass of 12 hydrogen atoms? 12 times 1.01 is 12.1. And last, what is the mass of 6 moles of oxygen atoms? That's 6 times 16, that's 96, right? So we add all that up, and that comes out to be 180.2 grams per mole. This is just like the calculation that we did for the carbon dioxide a minute ago, right? We're just adding up the molar masses of all the atoms in the formula. This tells you then it takes 180 grams to make 1 mole of glucose atoms. But we want to calculate the percentage composition. We want to convert this formula, which expresses mole ratios, into mass ratios, right? So what we're going to do is express each as a fraction or percentage of the molecular weight or formula weight. So for example, in terms of mass, what percentage of our mass was carbon? Okay, 72.06 grams divided by 180.2 grams, right? The 72.06 was the mass of the 6 carbons. The 180.2 is the mass of the whole thing. So what fraction or percentage is 72.06 out of 180? Divide, multiply it by 100, convert it into a percent. So 39.99% of our mass is carbon. Okay, what percentage of our mass is hydrogen? Right, we had 12 times 1.01 was 12.1. You divide that by 180, and you come out to be 6.71%. Right, so even though you have 12 hydrogens and only 6 carbons, mass percent wise, hydrogen is much lower because hydrogen is so light. All right, and then last, when we get to the oxygen, we take 96 grams, that was what? That was 6 times 16, divide that by the total mass times 100 to convert it into a percent, and you get 53.27. Okay, so what we did was we converted the chemical formula into a percent by mass. So as a check, we can check to be sure all these add up to 100, which they do. All right, so you could also do this problem in reverse. Okay, you could do this problem in reverse. We could take a formula. We could take the mass percents and convert them into a formula. So here we're talking about going from mass percent back to a formula. And there's a reason why you would want to do this. For example, if you're doing, it's very common. Let's say you're doing research in a lab, let's say, and you have a compound and you don't know what it is, and you send it out for analysis. They're not going to tell you, more than likely, they're not going to give you the formula for the compound. What they're going to do is an elemental analysis, and they're going to say it's so much percent carbon by mass, so much percent hydrogen by mass, so much percent oxygen by mass. So let's do this problem in reverse. So these are the numbers that we just used, our mass percents. So let's say your compound is 39.99% carbon, 6.7% hydrogen, and 53.27% oxygen, and we want to convert the mass percents back into a formula. Okay, so let's assume 100 grams of compound. That makes it easy because percentage is out of 100. So our percentages automatically become number of moles, right? So that means then that if we have 100 grams of compound, we have 39.99 grams of carbon, we have 6.71 grams of hydrogen, and we have 53.27 grams of oxygen. So what we have to do is now convert these each into number of moles, right? And we just covered how to do this at the start of the video. How do you go from grams into moles? You divide by the molar mass. So 39.99 grams carbon, how many moles is that? 6.71 grams of hydrogen, how many moles is that? 53.27 grams of oxygen, how many moles of that? We have to divide each by the respective molar mass. So we divide each by the molar mass, right? So 39.99 grams of carbon divided by 12.01 grams per mole, okay, is 3.33 moles of carbon. 6.71 grams of hydrogen divided by 1.01 grams per mole is 6.64 moles of hydrogen, and 53.27 grams of oxygen is divided by its molar mass of 16 grams per mole is 3.33. Okay, but you're saying, well, wait a minute, our initial formula was C612O6, not 3.33. So what you have to do is you can't have decimals. You can have decimals in a formula. We have to turn this into whole numbers. So you divide each by the smallest. Okay, in this case is 3.33. So 3.33 over 3.33 obviously is 1. 6.64 over 3.33 is 2. 3.33 over 3.33 is 1, right? This gives us the formula, empirical formula, CH20. Okay, and notice I said empirical formula. Okay, empirical formula. This procedure does not give you the molecular formula. It gives you the empirical formula. Okay, so what is the empirical formula? This procedure that we just used when we divided each by the smallest to get rid of the decimal, we reduced it to the simplest formula. And that's what the empirical formula is. Okay, an empirical formula expresses the simplest whole number ratio of atoms in a molecule. All right. It does not tell us about the number of atoms in a molecule, and it might or might not be the molecular formula. Okay, to determine the molecular formula, you would need additional information, like the molecular weight. Okay, now, if you know the empirical formula and you know the molecular weight, then you can figure the molecular formula. Yes. Okay. So it's possible for several compounds to have that same empirical formula. For example, formaldehyde, CH20, has this molecular formula. Its molar mass is 30.03. Acetic acid, C2H4O2, molar mass 60.03. Lactic acid, C3H6O3 is 90.08. Erythrose, C4H8O4, 120. Ribose, C5H10O5, 150.13, and then glucose, C6H12O6. But all these have the same empirical formula, CH20. We can divide this formula by 6, and we'll get CH20. Divide this formula by 5, we get CH20. Divide this formula by 4, CH20. But note, each of these is a multiple. Each of the molecular weights is a multiple of 30.03. Just like each of these formulas is a multiple of CH20, each of these molar masses is a multiple of the 30.03. Okay, so suppose we didn't know the compound was glucose and your empirical formula comes back to CH20. To know which compound you have for sure, you would also have to know the molar mass. Okay, and if you know the empirical formula and you know the molar mass, then you can get the molecular formula. So let's move to writing and balancing chemical equations. All right, so we talked about grams to moles and moles to grams. And then we talked about stoichiometry of a formula. Now let's talk about stoichiometry of basically chemical equations. And before we can get there, we have to start talking about writing and balancing chemical equations. So matter is neither created nor destroyed in a chemical reaction. All a chemical reaction does is rearrange the atoms that are already present. It does not convert one type of atom into another. Okay? So the same number and type of atoms must appear on both sides of the equation. If you have, let's say you have 6 carbon atoms on the left side of some equation, you're going to have 6 carbon atoms on the right side. So there's some rules here for balancing chemical equations. Okay, so first is that you can change coefficients in front of a compound or element, but chemical formulas can't be altered. So for example, you can't turn CO2 into CO3 just to make something balanced. Okay? We can't add products or reactants. You can't just arbitrarily add something to an equation to make it balanced. Okay? A third thing is a coefficient operates on all the atoms in a formula. In other words, when you put something, you're balancing an equation and you put something in front of one of your reactants, that number that you put applies to the entire formula, not just part of it. And then last, a balanced equation remains balanced even if you multiply all the coefficients by some number. Let's say we want to get rid of a fraction. Okay, so all this seems like a lot and it seems kind of formidable, but really it's not that bad after you work through a couple of examples. Okay, so let's start with some simple reactions here. Let's talk about combustion of methane. All right, so methane is a hydrocarbon, CH4. Now, we haven't really talked about types of reactions, but a combustion reaction is simply one where some substance combines with oxygen. All right, so we burn methane as CH4. It combines with oxygen to produce carbon dioxide and water, right? So we want to balance this equation. Well, clearly it's not balanced now because, right, we got 3 oxygens, 1, 2, plus 3 oxygens here and only 2 here. We have 4 hydrogens here and only 2 hydrogens here. So this is clearly not balanced. We have to get the same number and type of atom on both sides of the equation. So, say the oxygen are relaxed. Let's start with the hydrogen. So all of the hydrogen gets converted into water. Right? You only have 2 chemical species that have hydrogen in it. So if we have 4 hydrogen here, we're going to have 4 hydrogen here. But we don't have 4, we only have 2. Methane has 4 hydrogens, water only has 2. So what do we have to do? All right, we have to put a 2 in front of the H2O. Okay, so we're going to put a 2 in front of that H2O. Okay. Then we would balance the oxygen. Okay, so there's 4 oxygen atoms on the right side. Well, there are now, yes, after we put the 2. 4 oxygen atoms on the right side, but only 2 on the left. Okay, so we have to make the oxygen balance. We're going to put a 2 in front of the oxygen, okay? And we don't have to worry about the carbon because there's one carbon in CH4 and one carbon in CO2. So basically our equation is balanced. One carbon, four hydrogens to four hydrogens, and four oxygens to, okay, four oxygens. And that's basically how you do this. Okay, you have to put coefficients in front of the equations to make the atoms balance. You can't add something, you can't change a formula. Okay, so note again, what we're doing is we're rearranging the atoms that are already present. So here's a pictorial representation of this. We start with methane, we start with one methane, two oxygens, and oxygen is one of those elements that occurs as O2 molecules, right? So by having two O2 molecules, we have four oxygens. That produces one CO2 and two waters, right? So one more time, what are we doing here? All we're doing is rearranging the atoms that are already present. Right, so here the carbon is part of methane, and here the carbon is part of CO2. Okay, and here the hydrogens are tied to the carbon, and here the hydrogens are tied to oxygen. All we're doing is rearranging the matter that is already present. So let's look at a slightly more complicated example. Now let's look at combustion of octane. Okay, so oct implies 8, and octane is a hydrocarbon that has eight carbon atoms in it. Okay, it has 8 carbon atoms. So let's start with the carbon. Okay, usually you save the oxygen for last because both of these have oxygen in them. And we can't balance these without throwing the oxygen off. So you save the oxygen for last. We'll start with the carbon. All carbon atom gets converted into carbon dioxide. We only have 2 chemical species that have carbon in them. So if we have 8 carbons here and C8H8, we're going to have 8 carbons here. So we're going to form 8 molecules of carbon dioxide. Okay, now let's do the hydrogen. Okay, so we have 18 hydrogens. There's only 2 species here that have hydrogen in them. So all the hydrogen that's here has to show up in the water, right? So we have 18 hydrogens on the left side and that octane. So we have 2 hydrogens and a water molecule, right? So we're going to have to put a 9 in front of that water. Okay? And then last, we're going to balance the oxygen. Last, we're going to balance that oxygen. So we have 9. Remember when you put a coefficient in front of a formula like this, it operates on the whole formula. So when we put that 8 CO2 there, what do we really have? We have 8 carbons and 16 oxygens. So how many oxygens total do we have? 16 plus 9 is 25. But we have O2, oxygen, in the form of O2 molecules. If we put a 25 there, that means 50, not 25. And 2 doesn't divide evenly into 25. So it's semi-acceptable. This is the only case where a use of a fraction is in a formula, in a balanced equation rather, is semi-acceptable as with these diatomic ions. So we could write that as 25 halves. Okay? And basically then that's balanced. Or if that really bothers you, you can multiply by 2 and get rid of it. So you'd have 2, 25, 16, and then 18. And the equation would be balanced. Okay? So let's look at some. Before we go on and start talking about stoichiometry of equations. Let's practice a few more balancing equations. Balance a few more equations. All right. So combustion of, or not combustion rather, but the reaction of phosphorus pentoxide with water produces phosphoric acid. So if I were going to balance this, I would start with the phosphorus, right? So you have 4 phosphorus atoms. You have 4 phosphorus atoms in P4O10, but you only have 1 phosphorus atom in H3PO4. So we would have to put a 4 in front of the H3PO4, okay? By putting that 4 in front of there, remember that 4 operates on the entire formula. So we now have, on the right side, we now have 3 times 4, we have 12 hydrogens, okay? But we have H2O, there's 2 hydrogens in H2O, so we would react with 6 waters, okay? And basically then that equation is balanced. All right, let's look at the next one. The reaction of aluminum carbide with water to make methane and aluminum hydroxide. All right, so I'd say I'd start with the methane, CH4. Now we have 3 carbon atoms in Al4C3, but only 1 carbon atom in CH4, right? So to keep the carbon balanced, we're going to have to make 3 CH4s, okay? And we have 4 aluminums in Al4C3, but we only have 1 aluminum and aluminum hydroxide, right? So we're going to have to make 4 of those. And so lastly, it comes down to balancing the water. That 4 operates on this entire formula. So really, we have 12 hydrogens here, and 3 times 4 is 12 hydrogens there. So to make the equation balance, we would have to put a 12 in front of the water. It would probably be easier to do it from the oxygen, because the oxygen only appears in this one compound, right? So AlOH3, there's 3 oxygens per molecule of OH3. 3 times 4 is 12. And there's only 1 oxygen in water, so you'll have to have a 12 in front of the water. Okay? Third example, decomposition of potassium chlorate into potassium chloride and oxygen. That's kind of a neat reaction. You just heat it and it decomposes and gives off oxygen gas. Well, obviously we're going to have to make the oxygen balance. We have 3 oxygens in KClO3 and only 2 oxygens in O2, oxygen atoms, right? So to make the oxygen balance, we would have to have a 2 here and a 3 here. And then, because we have a 2 in front of the KCl, we'll have to make 2 KCl's and potassium chlorides, and that's it. That's balanced. Okay? Here we have another combustion reaction. In this case, it's the combustion of pentane, which is C5H12. Again, any combustion reaction produces carbon dioxide and water. So we have 5 carbon atoms in C5H12, but there's only 1 carbon atom in CO2, so we're going to have to make 5 of those. Okay. We have 12 hydrogens in C5H12, but there's only 2 hydrogens at H2O, so we'll have to make 6 waters. And then the last step is balancing the oxygen. We have 2 times 5 is 10, plus 6, we have 16 oxygen sitting over here. But we have oxygen in the form of O2. So we're going to put an 8 in front of the oxygen, and that's now balanced. Okay. Hydrolysis of boron oxide rather. Okay. B2O3 plus water becomes BOH3, which is boric acid. So we have 2 borons here and 1 boron here, right? So obviously we'll have to have a 2 there. Okay. And then our last step is to balance the hydrogen. So let's see, BOH3, there's 3 hydrogens, but we put a 2 there, so there's really 6 hydrogens on this side. Hydrogen is the form of H2O here, so we put a 3 in front of the H2O, and that's balanced. And then our last one here is the combustion of sulfur dioxide to sulfur trioxide. So SO2 plus oxygen becomes SO3. So this is really just a trick of making the sulfur is already balanced. So there's 1 sulfur here and 1 sulfur here, but the trick is making the oxygen balance because we have 2 here. We have 2 on this left side, and rather we have 4 on the left side and only 3 on the right side. Oxygen's not balanced. And the way we fix that is putting a 2 here, 2 here, and a 2 here. Right? So what do we got? We got 4, 5, 6 oxygens on the left side and 6 oxygens on the right side. And I've been doing this all along, and I hope I didn't confuse you. You don't have to write 1. So anytime if you don't see a number there, a 1 is implied. Okay, a 1 is implied, and that's why I said, okay, 2 times 2 is 4, plus the 2 makes 6. I'm assuming there's a 1 there. Just like there'd be a 1 here. Okay, there was a 1 here, and so on. All right. So we'll stop here. This is the first part of our video on stoichiometry. In the second part, what we're going to start looking at is the stoichiometry of chemical equations. In other words, if we have so many moles of this, let's say, how many moles of this would we make? Or if we start with so many grams of this, that's how many grams of this that we make. In other words, that's where we're headed with this.